We have the condensed formula. So the condensed formula is written in order to save space and time in the representation of the organic structure. It is a common practice to use condensed formulas in which the bonds are not shown explicitly. In using condensed formulas, normal atomic balances are understood throughout. As you can see, I have mentioned here the common condensed formula used while writing a structure: ethane, ethene, ethyne, methanol, ethanoic acid, methane nitrile, commonly known as hydrogen cyanide, ethane nitrile, commonly known as acetonitrile. Next up, we have the 3D structural formula, which you have seen in your books and all. So here is a sample. It's acetone, and the IUPAC name is 2-propanol. So a normal bond is shown by a straight line, and the dashed bond is shown by a dashed line. It means that the bond is away from the viewer, so you can say that the bond is into the paper. And then there is a wedged bond, which is the bond protrudes forwards. That means it's towards the viewer and it's effectively out of the paper. And normal bond means the bond lies on the plane of paper itself. So the dash bond is one where the bond is into the paper, and the wedge bond is one where the bond is out of the paper. Next up, we have the skeletal formula. It's another popular way of writing where you don't show the carbon, and skeletal formula shows the skeletal structure or the skeleton of a molecule, which is composed of the skeleton atoms that make up the molecule. As you can see, we have shown here acetone and propanol. So next up, we have the nomenclature. So how to name organic compounds? The primary goal of the International Union of Pure and Applied Chemistry, which is commonly known as IUPAC, is to create an unambiguous relationship between the name and the structure of a compound. With the convention established by IUPAC, no two distinct compounds have the same name. The IUPAC naming system greatly simplifies chemical naming. So now I have the steps in the naming. First, you have to identify the longest carbon chain containing the highest order functional group. Highest order functional group can be determined from the priority chain, which I have shown previous slides, and the longest carbon chain you have to decide, which is known as the parent chain, and will be used to determine the root of the nature. And if there are double or triple bonds between carbons, they must be included. And if one of the functional groups would provide a suffix for the compound, then the parent chain must contain this functional group. And you should always keep in mind that the highest priority functional group will provide the suffix. Second, you have to number the chain in the order of the longest carbon chain. The carbon numbered 1 will be the one closest to the highest priority functional group always. And if the functional group is not present, then you can mark it according to the longest chain of carbons. And if all the functional groups are the same priority, numbering the chain should make the numbers of the substituted carbons as low as possible. There should be less number of substituents. Next up, you have to name the substituents. So the substituents are functional groups that are not part of the parent chain, and the substituent's name will be placed at the beginning of the compound's name as a prefix followed by the name of the longest chain. As you can see, these are the commonly used substituents: tertiary butyl, neopentyl, isopropyl. Isopropyl is one where the two methyl groups are attached to the same carbon. Neopentyl is one where a carbon is attached to more than 3 functional groups. And tertiary butyl, where as you can know that our carbon is attached to 3 methane. Next up, you have the secondary butyl, and next you have the isobutyl. Fourth, you have to assign a number to each substituent. You have to pair the substituents that you have named to the corresponding numbers in the parent chain, and multiple substituents of the same type will get both the di, tri and the tetra prefixes that we have previously noted, and also a carbon number designation even if they are on the same carbon. So last but not the least, you have to complete the name. Names always begin with the names of the substituents in alphabetical order, with each substituent preceded by its number. Prefixes like di, tri and tetra, as well as the hyphenated prefixes like n, tertiary are ignored while alphabetizing. You should always not consider the di, tri prefixes. Next, non-hyphenated roots that are part of the name, however, are included. These are modifiers like iso, neo and cyclo. The numbers are separated from each other with commas and from words with hyphens. Finally, we finish the name with the name of the backbone chain, including the suffix for the functional group of the highest priority. Here's an example. You can see there's an ethyl group attached to the 4th carbon, so you have written as 4-ethyl. Then there's an isopropyl group at the 5th position. Its name is 5-isopropyl. E is first in the alphabetical order, next comes I, and then you have 3,3-dimethyl octane. Since this is the 8th carbon group, that's why it's octane. Octane means 8, and since there are 2 methyl groups attached to 3rd carbon, it's known as 3,3-dimethyl. and the words are separated by hyphens, and the individual numbers are separated by commas. You can circle or highlight the parent chain in each of the following compounds as a practice. This is a practice exercise which you can do if you want. Here are some popular compounds which you should know how to name. Here's the answer key. So these are some common name of aldehydes. Methanol, ethanol and propanol are referred to almost exclusively by the common names, which is formaldehyde, acetaldehyde and propionaldehyde respectively, rather than the IUPAC namings. So you should always remember this while writing a compound: formaldehyde, acetaldehyde and propionaldehydes. Some commonly named carboxylic acids are methanoic acid, which is commonly known as formic acid, ethanoic acid, which is commonly known as acetic acid or vinegar, and you have propanoic acid, which is commonly known as propionic acid. Next you have the carbon, carbon and carbon. This is the review on the importance of carbon and the principles involved in the hybridization and bonds. So why carbon? Molecules with carbon are organic. Carbon dioxide and molecules without carbon are inorganic. Why carbon is important? They are versatile. They can form up to 4 bonds, which is a property known as catenation, and they can also form rings or chains. They can form infinite number of bonds. Bonds formed high in energy, for example in diamond. Diamond is the most stable form of carbon. The most stable is the Buckminster fluorine. Functional groups in organic molecules are less stable than the carbon backbone, but are more likely to participate in chemical reactions. You should always determine the characteristics and chemical reactivity of the organic molecules. So the principles involved. There are 3 main principles which are followed. First is the Aufbau principle, second is the Hund's rule of multiplicity, and third is the Pauli's exclusion principle. I will just give you a brief on it. So Aufbau principle is this: electrons will always successfully occupy the available electrons in the increasing energy. In short, the lowest energy orbital should be filled first. Hund's rule of multiplicity is that every orbital must contain at least 1 electron before filling up another orbital, and when there are more than 1 orbital at a particular energy level, only 1 electron will fill each orbital until all the orbitals has 1 electron each. After this, pairing will occur with the addition of 1 electron to each orbital depending on the pairing energy. Third, we have the Pauli's exclusion principle, which is our last principle and a very important one. In a given atom, no 2 set of atoms can have the same set of 4 quantum numbers. Therefore, each orbital can only hold 2 electrons and not more than that. So this is the hybridization which you commonly know. All atoms undergo hybridization. As you can know, like for example, red plus white forms a color pink. What is the purpose of hybridization? So the purpose of hybridization is forming equivalent orbitals. Orbitals with the same shape. As you can see in the sp3 hybridization of carbon, the ground state is 2s2 2p2. As 1 electron gets excited, the 1 electron jumps to the empty 2p orbital from the 2s orbital. Now the sp3 hybridized orbital is as follows. You can see the sp2 hybridization of carbon and also the sp hybridization of carbon respectively. Here is the tetrahedral, trigonal, planar and linear angles. For tetrahedral, the angle is 109.5 degree. Trigonal, planar, the angle between the 3 carbon is equal and each is equal to 120 degree. For linear, it's 180 degree. For hybridization state, as you just saw for sp3, there are 4 hybrid orbitals, as you can see denoted by the green color. No 2p orbitals are left over, and geometry around the carbon is tetrahedral. sp2 has 3 hybrid orbitals and the geometry is trigonal planar. sp has 2 hybrid orbitals and the geometry is linear. Tetravalent means carbon generally forms 4 bonds. Trivalent, nitrogen is a trivalent element. It generally forms 3 bonds. It depends on the valency. Divalent, oxygen generally forms 2 bonds, and monovalent is halogens and hydrogen. So next up is the most important part of the organic chemistry, which is the isomers and the stereochemistry. So here we will talk about the definition, types and classifications. So what is stereochemistry? The branch of chemistry concerned with the 3-dimensional arrangement of atoms and molecules and the effect of this on chemical reactions. So the branch of chemistry that studies isomers, so you will ask what are isomers, and the property of a compound to have isomers. We have some important notes to take. We need at least 1 sp3 hybridized carbon to represent molecules as 3D object. And we should always draw a 3D diagram for stereochemistry and not a 2D drawing, since in that case you won't be able to show the wedge and the dashed forms. What are isomers? So isomers is each of two or more compounds with the same molecular formula but a different arrangement of atoms in the molecule and different properties. They can differ in the arrangement of bonds. You can refer to actual bonds between atoms. Isomers with a different connectivity of their atoms. Configuration refers to the permanent spatial positions of two isomers with the same attachments. Two configurational isomers are never identical to each other. Conformation refers to the temporary spatial positions, and the two conformational isomers can be identical at one point. So isomers are mainly divided into two parts. One is the structural or the constitutional isomers, and the next is the stereoisomers. So the constitutional isomers depends on the arrangement, and the stereoisomers depends mostly on the arrangement in the space, which is the spatial position. So constitutional isomers are mainly of three types: skeletal attachment, positional, and functional. Positional, skeletal is determined by the attachment of the carbon. It can be pentane, isopentane, neopentane. Positional is defined by the placement of the functional group, and functional is the actual functional group which is present in the compound. It can be propene, it can be a cyclopropane, but the atoms used are the same. Stereoisomers is the spatial position. It can be mainly divided into two: configurational and conformational. So configurational is the permanent spatial difference, and the conformational is the temporary spatial difference. Configuration are mainly divided into two parts: optical isomers and geometric isomers. Geometric isomers are mainly unsaturated or cyclate, as we discussed previously in the first slide. Optical isomers are mainly tetrahedral, which are again divided into two types: enantiomers and diastereomers. Enantiomers are the non-superimposable mirror images, and diastereomers are the non-superimposable and non-mirror images of each other.